Hello everyone. So today we are going to solve Gigs for Gigs this problem, mean as moments to connect to a graph. What we have given is we have given a number of vertices and as is that are connected in this graph. What is the problem statement is? Problem statement is telling like we have different components in our input graph. Like as you can see in this example, we have this component and we have this component. Component I mean to say is that are the connected vertices that can be considered as a one of the component. So we have to connect every vertices if possible. We have to connect every vertices of the given input for the n vertices from the extra edges that we have given in this input graph. What I mean to say in simple terms is like as you can see in this component 0, 1, 2 we have 0 is connected to 1 and 2 both, and 1 is connected to 2, and 3 is not connected to any of these vertices. So we have to try to be connect number 3 vertex to the this particular component 0, 1, 2 component. How we can do that? We can remove this as 0, 1, or we can remove this 0, 2, or we can remove this 1, 2. If any of that is if I'm removing, this component still be connected, and I can use that as particular to connect with the vertex 3. So let's go to the board. What I mean to say is we have given this like example. We can take this and first we will understand like what is the problem statement so that it will be clear. Uh, this we have given and okay. So we have 0, we have 1, we have 2, we have 3. So if I'm using this, let's suppose if I'm removing this 1 and 2 edge, and I will use that as particularly to connect between 2 or 3 or 1 to 3. Like let's suppose if I'm using this. So the whole vertices, four vertices that we have given, 0, 1, 2, 3, all are connected now. And I'm using for that one operation. Why one operation is because I'm removing one edge and I'm using that one edge to connect to the components. So we have given this, and we have to output like how many edges we can use that, how many minimum number of the operations that we required. The other point is if it is not possible to connect the complete graph, there can be a possibility like you cannot if the input example is 0, 1, 2, and this one and 3. So in this case, we cannot remove any of the existing edge. Like let's suppose if I'm removing 0, 1, then I cannot connect with 2 or 3 because then one will be the as a separate component. That cannot be possible. So in this case, the output will be 0. Okay, hope you will understand this. Let's take one more example so that it will be more clear to everyone. Um, okay. Consider we have edge edges are like 7, 4 and 2, 7, 7, 9, 3, 1, 9, 8, 6, 5, 0, 2, and 8, 6, 2, 4. This is a very interesting example. Let's consider this, how it will work. So we have and we have given the vertices as consider 10 vertices we have. So I will take n equals to 10. So in this case, consider we can draw the graph like this. So 0, first start from the 7. So like how I will draw the graph, like number 7 is connected to the 4. Okay. And 7 is connected to 2. Okay. 7 is connected to 9. Consider this here, it is 9. And 3 is connected to 1. Consider 3. And this is 1. 9 is connected to 8. Okay. And 6 is connected to 5. And consider there is some 6 that is connected to 5. And 0 is connected to 2. So here it is 0. And 8 is connected to 6. So 8 is connected to like this 6. and 2 is connected to 4, 2 is connected to 4. So here you can see there are how many number of the components are there in this graph. There are two number of the component, because one is this component, this is complete one component, this is complete one component. And how many edges we require? Okay, so first of all we have to understand how many edges we required to extra edges that we can use to connect these every vertices in our graph. So basically, if the number of components, if we are able to find out the how many number of components we have, so we need to require like this one edge to connect the two components. So basically, if the number of components we have in our input graph, that is n, so we require n minus one as the extra edges that we require to connect the every vertices in our application in our input graph. Coming to the point, how we will find the number of components, that we will see in some time, but the logic behind will be this one. Coming to the next point is how you will find out which one is pointing to which one. Like I mean to say like 7 comma 4 is one edge, but how would you make sure like they are belonging to one component and you can use those extra edges? What are the extra edges that we have? How we will find out? So for that, what we will do is consider this example, same example like 7 4. So if we are drawing this 7 4, we can say consider a array we have we need some we need to find out, okay, 7 and 4 are connected to something, are connected. So to identify they are connected or not, we can use some type of array. Okay, we have the n size array we can take, and we will say, okay, if 7 and 4 are connected, so we can find out like, okay, 7 is connected to 4. We can find out from that array, and we can say, okay, if both elements are connected, it means this as is required because their parent is different. Why the parent concept is came, like let's suppose 7 parent is 7 initially, 4 parent is 4, and if I'm connecting both of them, it means now they have connected, so their ancestor is same. 7 and 4, we can say their ancestor, let's suppose 4, lesser value we will take or greater value as you want, but yeah, I'm taking the lesser value, so you can say like 7 and 4, the parent is 4. So from this we can identify, okay, their parent is same, it means their ancestor is same, and this as is required because initially their parents are different. So you will better understand, like consider we have this array, and initially every element is like from 0 to 9, because 10 is the vertex. 0 to 9 we have the number of the vertices. So I can say the parent of initially every vertices have their own parent. So 3 4 5 6 7 8 9. So these are the initial parent for everyone. We can say for 7, the parent is 4. So what will be the 7? This will be the, so we can change this, like let's suppose it is a parent of the 4. Coming to 2 and 7. So now if I'm going to connect 2 with the 7, so it means 2 and 7. Now the parent of the 2 is 2 and 7, the parent is 4. Okay, but we can say if they are connecting, so it means that ancestor should be the same. So to make the ancestor same, so we can say 7 parent is coming to with 2. Okay, but the 7 parent is 4, and 4 can have itself have some parent, right? So there can be a possibility. So what we will do is we will find the ultimate parent. So what will be the ultimate parent of 7 in the current architecture? That is 7 parent is 4, 4 parent is 4. So we can say 7 ultimate parent is 4, two's ultimate parent is 2. And how we will connect them? So we will make the fourth of the element as the 2. So basically what I mean to say is, so it will become like fourth element will become as a parent as 2. So it means we are saying as 7 parent is 4, fourth parent is the 2, and 2's parent is 2 only. So we are finding going to be basically ultimate parent, and this will help us to just identify how we are going to solve the connection problem in this. There is nothing much like 7 comma 9. If you will see what is the 7 comma 9 says, like again 9 ultimate parent is 9, seventh ultimate parent is 2, because seventh parent is 4, parent is 2, and two's parent is 2. So we can say ninth parent is also as 2. Similarly, we can we can do, and we can make this parent array, and we can identify easily, okay, which one are the both are the connected. And let's suppose consider this example 2 comma 4 quickly. If we will go with this, so we will identify, okay, fourth parent is ultimately parent is 2, and two's parent is also ultimately as a 2. In the now like if you will draw completely, you will see fourth ultimate parent is coming out as like 2, and two's ultimate parent is also 2. So if both are the ultimate parent is same auto directly and both our ancestors are same, why do we require this as? This can be an extra as considered, right? So this is an extra as, so we can remove this extra as and we can use somewhere that we have to require. And we can use this as to connect between the 3 and 1. So this is the like architecture or like idea behind the solving this problem. Uh, Coming to the how we will solve this, first we will write the like basic points what we require. So basically, we require some of the points are first we need to find out the how many extra edges are there so that we can use them. So extra edges are there in our graph, and to identify the extra edges, we need to use some parent concept like ancestor. We need to find out for every node, and for that we will use some ultimate parent array or something, and we can use like this array to identify. Okay. Coming to the next part, we need to find out how many edges we required in our application to connect. So how many edges we need to connect this graph. That will be our number of components. We can say -1. Okay. Coming to this, to take this example, we can write. I will write the code in Java, but you can replicate this code in other language that you are preferable for you. So we have the n and edges. What we are going to do first, we will require how many extra edges are there in our application. Okay, so what I will do is let's consider I will make an as a parent array that is initially is of size n, and I will initialize this parent array. I'm going to write the code in such a manner that if you are a beginner, if you don't know the graph concept clearly, still you will understand this problem and how will you going to be approach this problem in your interviews and your problem statements. So what I will do is parent of I equals to I. This we have discussed like initially parent of every node is itself the node. Okay, itself they are the parent of itself. Coming to the next point, how many edges? So what we will do is we will iterate over the initial input array. Uh, and what I will do is consider we have source vertex as is of I of 0, and we have destination vertex as consider this one. So what I'm going to do is I will first check, okay, what are the ultimate parent of both source and destination. So let's suppose I will get as the ultimate parent for this one. So get ultimate parent of vertex u in this parent array. What is the ultimate parent? And what is the ultimate parent of this one? Uh, Destination vertex. So once I will find out the ultimate parents, I will check quickly like are these ultimate parents are equal? If the ultimate parents are equal, it means their ancestry is already same, then why we require this extra as? So what we will do is we will take a variable that is uh, extra as is count that is initially is 0. And what we will do is we will take this and we will increment because we found a extra as. But coming to the point, if the ultimate parent is not same, then we have to make now the we have found a connection between them. So we have to make their ultimate parent is the same. So to do that, what I will do is I will take as the lowest value so that it will be consistent in our application. So I will check if my ultimate parent of the vertex u is less than ultimate parent of the vertex v, then I would make the ultimate parent of vertex v to the ultimate parent of vertex u. What I mean to say is parent of PV will become as uh, PU so that now the connection is made, and same for parent of PU. If that not the case, then I will make as a PV. It's simply a logic that to find out the how many extra edges we have. Next, what we will require is how many extra edges we require. So what are the number of the components in our application? How we will find the number of components that I will also tell. So get number of components in our application that is n comma as is and whatever and how many as is we required. So as is required, that will be my number of components that I have minus 1. So this will give my as is required. This I have the extra as is count. So our problem statement is currently say if it is not possible to connect the graph, when we will be not possible to connect the graph, when we have the like extra as is less than the as is required. Like let's suppose extra as is we have 5, but as is required is 7. In that case, we cannot use those extra as is, right, to connect this complete graph. So what we will do is in that case, if like if my extra as is count, it's simply less than my as is required, I would say this is not a possible solution. And otherwise, it means this is a possible solution. So what I will do is I will return the extra as is count that we have and as is required. How many edges we required in this. So whatever the minimum value is, that will be our answer. That will be the minimum number of the operations that we have to do. Okay, because that number we will give. In that case, we need this get ultimate parent first thing. So I will quickly write this function get ultimate parent. We have some vertex and we have parent. How we will find the ultimate parent? Coming to that part is how we will do that. Consider we have this array, that parent array we have. And in this parent array, we have checked like, okay, seventh parent is 4, fourth parent is considered 2, and two's parent is 2. We will going to be iterate till it is not equal to itself. Like let's suppose in a simple language, like consider this we have a vertex 7, this we have a 4, this we have a 2, and 7420 like this. 7 parent is 4, but fourth parent is not equal to 4. So it means there is something else parent. So fourth parent is 2. We will go to 2. Two's parent is not equal to 2. So two's parent is 0. 0 is not equal to 2. So it means something there is a parent of 2 is also exist. We came to 0. So zero's parent is 0 only. It means it is the upper level node that we can say in our this in this design. So what we will say is seventh ultimate parent is 0. So for do that, what I will do is I will check quickly while uh, parent of source is not equal to source, then I will do is what will be my source is my source will become parent of source. And finally, I will return. It means their parent of source and source. It means 0, parent of 0 is equals to 0. Then it means it we will become we reach the upper level node. So we will finally return that source. Coming to the number of components, how we will do that? There can be multiple approaches. Like some people are using the number of to finding number of components if they know the graphs and they have done like we can use some adjacency list. We will first prepare the adjacency list and we will do some DFS algorithm over there. But from this example, as we have now have the parent array, ultimate parent array, we can use this directly to find the number of the components. But as per my suggestion, if you are a beginner level and starting the DSA, then I would suggest you will go with that DFS approach. And to optimize that code or to reduce that part specifically, you can move to this part. So coming to this, how you will use the parent array. Now understand this concept. Okay, we have this component and we have this component. Finally, ultimate parent is what is this? Like this is containing the ultimate parent of all of those vertices, like ninth ultimate parent, whatever the it is in this graph, that is, and 1, 3, that is. So coming to the like, let's suppose we have some data structure in which we will first come to 9, and let's suppose every vertices of in this graph as the ultimate parent as 0. So how we are going to this is like ninth ultimate parent is 0. So we will say, okay, ninth ultimate parent is 0. Seventh ultimate parent is again 0. And then we don't need to store, right? Because it is already there. So we can say it is some data structure we are using and that will identify. And to unique identify, we will use has set. And fourth ultimate parent is 0 again. Then we don't need to use eighth 0, 2, 0, 6, 5. Everyone is the 0. So we cannot use this. Coming to 3, but 3 ultimate parent is considered as 1. So in that case, what we will say, okay, 3 ultimate parent is new values came. So 3 ultimate parent is 1. And 1 ultimate is parent is 1. So again, we have the find out, okay, there were 2 components in this application. We will use this simple algorithm to find out the number of components. For that, we need the, as we discussed, we need the parent array also. We don't need it as is. as we have made the parent array. So what we will do is uh, private int number of components. Again, it depend on how you going to write. If you're using as is, then you need to make adjacency list, and you can use DFS or BFS, whatever the approach that you are comfortable with. Coming to this part, to go, okay. So number of components we would say initially are 0, and I will go with the every vertex. I will create one as set so that I will store the unique values to quickly find out. And so what I will do is I will check the ultimate parent of this vertex. So ultimate parent for uh, get ultimate parent for this vertex, that is I can use, and we will just insert this ultimate parent to our set. And finally, whatever the set size is, it will return as the number of the components. And number of components will give us the edges required, and we will just quickly check how it will be. I think should work. Let's try with this put. Okay. Uh, get ultimate parent number 16. Okay. Oh, this is incompatible int cannot be converted to int. Oh, sorry. Uh, yeah, this is working. Coming to this example, we can try with some put. We have 10 vertices. We have edges is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 edges. And 7, 4, 2, 7. That is 7, 9. Next is 3, 1. Next is 9, 8, 6, 5. 0, 6, 2, 4. Looking for this. Yeah. 0. Okay. Sorry, I missed 9. We have. Yeah. So one edges is there and one operation is required. Okay. Try to submit this solution. Yeah, it is working fine. Okay. So thank you. If you understood the problem, if you get some like how to solve this problem, if you get the logic, please like, subscribe and comment if you have some questions. We will discuss more on that. Thank you.